Hello, this is Dave Davis, silage expert, and today I want to talk about why we should be applying 1 million bacteria per gram of fresh forage within our silage inoculants. And my aim in this short presentation is to show you why the science on 1 million homofermentative lactic acid bacteria are needed, and to actually debunk the reasons why some companies say my additive doesn't need 1 million, but it still works. So this is an electron micrograph of one of the commonly used bacteria, Lactobacillus plantarum. And we need that inoculation rate of 1 million because there are high levels of natural undesirable flora on the crop. Enterobacteria, Clostridia, yeasts, and molds being the main ones, and relatively low levels of the lactic acid bacteria. And speed of fermentation is important because, firstly, it inhibits the plant enzymes, which have an optimal pH between 4.5 and 5.5, and these actually are the things that start to break down the protein into amino acids. And it inhibits all the undesirable bacteria quicker, increasing the sugar, protein quality, and intake. And proteolysis is a two-step process. So the first step is actually the plant's own enzymes converting protein to the amino acids. And the step two is the microbial conversion of those amino acids to things such as amines and ammonia. Now, this is a study done some years ago on a funded program from independent sources, and the lines show the enterobacterial populations over the first 16 days. The inoculated, the yellow line there, is 1 million homofermentative bacteria, and there we have the untreated, and we can see we have an extended growth at very high levels. So 10 to the 6 here, that's 1 million. So within the first 2 days, the enterobacteria on that untreated goes to 1,000 million bacteria in every gram. Whereas with the inoculated, it drops very quickly to 0. So that speed of silage fermentation is like an obstacle race. And what do I mean? Well, basically, when we get protein breakdown, this is an intact protein molecule shown here, and each of these is an individual amino acid, and then on the end of those we have an amino group. And that amino group is neutralized by the acid that we're producing. So when we have intact protein, one acid molecule is needed to neutralize that amino group, but that acid molecule is no longer available for acidification and preservation of your crop. So if we have a lot of breakdown, so we have the plant enzymes and the enterobacteria and clostridial enzymes breaking down that protein, we end up in a situation where we have lots of short peptides or free amino acids or even ammonia, and each of them has this amino group on the end, which when we produce our acid, the acid is neutralizing that and the pH is not going down. So the more protein breakdown, the more acid we need to neutralize that, that's used to neutralize that, and the less there is for acidification of the crop. So like I say, the quicker we bring the pH down, the quicker that stabilization of that silage happens, the less acid we need to produce. So like I say, an obstacle race. The quicker you go, the less obstacles, the slower you go, the more obstacles. Then we look at the typical bacterial growth curve. In this, we can see that we have a lag phase, a very rapid reproduction phase of the bacteria, a stationary phase, and a death phase. And this speed of the growth of the lactic acid bacteria is very important within that fermentation. And many of the inoculants, and most of the inoculants, have a very similar rate of growth. So speed of their growth is the same or similar whether there's 1 million applied, 250,000, or 100,000. So this is a study, again, done a number of years ago, showing untreated, there in the red line, 100,000 and 1 million per gram on the speed of fermentation and how quickly we come below that low pH of 4.2. The more bacteria, the quicker that pH comes down. So if we consider we're inoculating with 1 million, these bacteria under ideal conditions will divide every 30 minutes and double in number. So after 30 minutes, our 1 million bacteria is now 2 million in our silage. If we started with 500,000, it takes 60 minutes before it gets to 2 million. If we're at 100,000, which many additives are, it's 126.5 minutes before it gets to that 2 million. That doesn't sound like a lot, an extra 100 minutes or so. However, we need to consider what's happening with our 1 million inoculant. So if we now look at another table with a third column, as I said earlier, our 1 million after 30 minutes is 2 million. Our 250,000 takes 90 minutes to get to the 2 million, by which time, if we'd inoculated with 1 million, we'd have 8 million bacteria. And our 100,000, in that 126.5 minutes, our 1 million inoculation rate bacteria is now at 18 million, whereas this one is still at 2 million. So if we inoculate with 1 million, we're always ahead, and we're always playing catch up when we inoculate with less. When we're playing catch up, we've got more of those obstacles in the way of our fermentation process to reduce the fermentation even further, use more sugar, need more acid to be produced, and produce a lower quality silage. This is a more recent trial than the one I showed previously. It was high dry matter grass. It was around 50% dry matter at ensiling, and we had untreated 100,000, 500,000, or 1 million, and these were all the same inoculant. You can buy them on the market from some companies at the 100,000. Other companies are selling at 500,000, and the best companies are selling at 1 million. But it's exactly the same bacteria. And we can see pH decline. Here, untreated, slow pH decline. It was slightly faster with the low level of inoculant, but with the 1 million, it was significantly faster. And this is the same additive. So no question about this multiplication, faster speed of multiplication. It's all about the fact that we're adding 1 million bacteria. So in summing up, if we inoculate with 1 million homofermentative lactic acid bacteria, we will speed up the preservation process, which reduces the amount of protein that's broken down. Intact protein is a better feed for the rumen, a better feed for the ruminant, reduces ammonia production, increases sugar content of the silage because less of it is needed for the fermentation process, and it reduces the dry matter losses. Thank you for listening.